Today, I'll be talking about materials of nature. Before I go, I just want you to sort of get an idea. The word circularity, right? And everywhere you are now hearing the circularity, this and that. How many years back probably we were in natural circularity? Anybody can guess? If you natural materials. And that means how many years back? You just project 1,000 years, 2000s. So we are redefining the nature's circularity, and I think we are predicting about 8,000 years back, if we go, the nature was in harmony. And then through that, the Anthropocene structures changed over the times, and now we are living in an era where we are seeing all these, emissions and other aspects of the climate change, and we want to go back to the circularity. And so the age and education tells us how this material age changed from 8,000 years to the Stone Age, then your material age, which I say the fossil fuel age, and then we are transitioning to the pseudo-natural age. So my 35 years of my research, actually in various countries, taught me one thing. If you are not exposed to extreme poverty or extreme climatic situation, you are underestimating the effect of climate change. And I felt that, and I'm telling you, I was not that poor. I had food, but every day when I transported from my place to my college, I had really carbon particle going inside my. So having said that, first project I did in my PhD with Volkswagen. In Germany, they gave me the project. Project is to how to transform tires, into a woody materials. That was my project. And I liked that project because before that, I was working in a cable company, and I was in Cork as an insulator for the cables. So I said, well, I know this, so I'll do that. So since that time, I always look for natural materials. And today, after 35 years, I strongly believe that nature can teach us anything and everything to reverse back to the natural circularity. So I wanted to give you two case studies, which we have done, not myself, my students and my researchers over my span of time. I'll give you two examples today. How actually nature delivers science and how that science can be then transported into reality. So I talk the boundless functions of natural materials. Anywhere you go, you see something is happening. It's just a dew is falling on a leaf, and that drop is always standing. It's not falling. Why? There's a surface tension. So once you understand the science of Mother Nature, you can create things which are actually natural in many aspects. So we are working on this for the last 20 years in Faculty of Forestry, actually, and then when I'm transferred to the engineering. So let me give you two examples. So if you have a natural material, most abundant will be your plants and trees and whatever, right? So if you look at the construction of this material, you can find three different components. One is, you have stems. If you take stems are essentially three things. It has fibers, like you eat fibers, nutrition, right? Put fiber because they will give you good sort of a probiotic approach. And then you have another thing which we call adhesives. And in stem, because stem has to stand, so you need adhesives that is strong enough that it can stand. And it's called a glue. Glue is called gnine. It's a aromatic natural material which has the capability and function to make that stiffer and functional. And third component is the carbohydrate. You're eating carbohydrates. Some of them are say ketos. I don't eat carbohydrate. Carbohydrate is essential. Complex carbohydrates is the key for our digestion system and nutrition system. We should not forget that. And these plants have all three things. And if you have all three things, you can literally substitute anything and everything you see in today's material world. So I take two examples. One is this fibrous part. You give me a straw, whether it's coming from hemp, which is marijuana, or it's coming from your tree or bark, or even it's coming from something else from your kitchen waste. science can extract these fibers. Now, where you want to go? First, you have to understand the science behind formation of this fiber. So you have to go to biogenic pathways and roots and understand how you are having the soil and these nutrients and how its pathogenic way allow you to form these molecules, which are called cellulose, lignin, and carbohydrate. Once you follow that pathway, if you can reverse engineer that pathway, you probably can develop a numerous number of functional materials. So with that, we're taking only the fiber. It has been demonstrated in the last 20 years research that you can cover almost anything where you can see an flexible electronics, like, whatever you see in your cell phones and others. You can look into water treatment facility, membranes, bacterial membranes, which will give you the purified water, which is scarce right now, energy device, biomedical device, and so on and so forth. So this is one of the platform I want to move and talk about it. So one of the fundamental things we learned that when you have nutrients and you have CO2 and you have water, this forms a chemical called cellulose, right? And you have this molecule, and this molecule has functionalities like hydroxyl groups. Now you can change this functionality of the hydroxyl group, and you can make a large number of materials. So this is one of the work we have been doing for the last 15 years, and it shows that you can do printable ink for thin film transistors, light emitting device, and energy devices. Now, for these things, I wanted to tell you one more thing. The core idea of this is understanding molecular dynamics of the material. Without understanding those molecular dynamics, you won't be able to make that thing happen. So at the end game, I want to give you an example. So what happens if you understand the science behind that and you really step by step follow the science, you'll be able to make a material which are almost 90% made from these natural materials. And this is an example which I developed 2008. So you can go back 12 years, and this is a flexible material which has these fibrous materials, and it can function as good as any other display system. Next thing, I'll take 2 more minutes to talk about the carbon. We all talk about graphene, graphite today. You know that all battery systems, they have graphites. Now, graphites are scarce because we need lots of batteries, lots of fuel cells. Mother Nature gave us lots of carbon if we can manage it well. So I give you some example how we stand and where we go. So if you understand the again, pathogenic way of making this, we can transform some of this biomass into such type of material. And that particular material will lead to a material which can give you some of the things which probably you don't think that is feasible. It can make a sensing material, it can make a battery, it make a fuel cell, and it can make many, many other things. I'm not going to go to details. I just wanted to show you how intrigued is the science once you understand science and how science can be transferred. So if you know the carbon material in the atomic level, and you can design the atomic characters of this carbon, you can define your material. I'll show you 3 different projects and display it here. So this is one of the things. This is one of my students. He did his final PhD, and I asked him to demonstrate how your spruce waste material can be transformed into an electrical conductor. So this is hard project, which is showing at a tiny scale, right? It was before 7 years probably, and it demonstrated. Today, as I speak, we were able to develop a material which is very close to formation of a battery. And I'm just, so this is the same student. I sent back after getting a PhD, I say, you have to make a battery. I don't care how you do it. So we sent them to a facility we work with, and this particular carbon is coming from birch. It's a waste birch material. We designed the carbon molecule in a way that linear difference between 2 layers of carbons is less than 3.4 nanometers, which means the 3.4 Armstrong. That gives the highest conductivity of this material, and that led to the formation of cathode. So we just displayed a pouch cell and the formation of a battery material out of it. So these two examples are mind-blowing, and I think there's a lot of media right now to move it to the another direction. So I'm not going to go to detail of that, but I just wanted to say, think natural, practice natural, and eat natural. That's all. Thank you very much.